In the last video, we talked about the photoelectric effect, a discovery that completely changed how we think about light. Classical physics said that light was a wave, but the photoelectric effect showed that light also behaved like a particle. A photon with an energy E is equal to h nu. This raised a fascinating question. If a wave, if a wave like a light can behave like a particle, could a particle like an electron also behave like a wave? That's exactly the bold idea proposed by 1924 by a young French physicist named Louis de Broglie. His hypothesis became one of the cornerstones of quantum mechanics, and today we'll explore what it means, why it works, and how it was proven. De Broglie proposed something revolutionary. All matter has a wavelength. Not just light, but electrons, protons, atoms, and in principle even large objects. His formula for these wavelengths is surprisingly elegant. Lambda is equal to h divided by p, where lambda is wavelength, h is Planck's constant, and p is the momentum of the object. This simple equation says that anything with momentum, anything that moves, has an associated wavelength. The smaller the momentum, the larger the wavelength, and the larger the momentum, the smaller the wavelength. For everyday objects like baseball, the momentum is huge, so the wavelength is very small, a tiny, far too small to observe. But for very small particles like electrons, the momentum is small enough that the wavelengths become significant, and that wave nature starts to matter. This idea didn't come out of nowhere. De Broglie looked at what we had already learned about light. We knew that photons behave like both like waves and particles. De Broglie wondered, if waves like photon have momentum, maybe particles like electrons should have wavelengths. It was a bold symmetrical argument. If nature treats wave like a particle, maybe nature also treats particle like wave. And amazingly, this prediction was spot on. The Broglie wavelengths also explain why electrons can occupy certain orbits in atom. The electron's wave must fit neatly around the nucleus, forming a standing wave. If the wavelength doesn't fit, the orbit simply isn't allowed. This simple idea helps explain why atoms have discrete energy, a concept classical physics could never account for. So, what's the deeper meaning of de Broglie wavelengths? It tells us that matter isn't just made of particle or wave, it's made of something deeper that behaves like balls. When momentum is small, the wavelengths become noticeable, and the wave becomes dominant. When momentum is large, the wavelength shrinks, and the particle nature takes over. It's a continuous transition. The universe quietly switches between wave like and particle like behavior depending on scale.